Hello, everyone, and welcome to Nanome. My name is Carla, and I'm a medicinal chemist, and I'm joined by Mike, also a medicinal chemist. And today we are going to be talking about this Nature Communications paper on the subject of BCL-2 in complex with an antagonist drug called Venetoclax, which was developed at Abbvie.
Yeah, this is going to be a really exciting discussion today, Carla. So here in gold, we have the structure of BCL-2, which is also called B-cell lymphoma 2 protein. And you find this on the mitochondria. It is a pro-survival protein. So it's found overexpressed in a number of cancer cells, including those that cause chronic lymphocytic leukemia, or CLL. And the way it works is it actually binds up peptides, these BH3 peptides, such as BAK and BAX, and keeps them from doing their job. And what they do is they're able to bind to the mitochondrial membrane and start and permeabilize the membrane, which starts the cascade towards cell death. So by keeping these peptides from doing their business, BCL2 promotes survival. It's also called anti-apoptotic.
Right, and Venetoclax, I guess, was developed as an antagonist to complex with that binding site. So we're going to take a look at the crystal structure that was solved by the team. And just want to point out some interesting features of it. So Venetoclax actually binds to two pockets called P2 and P4, and P2 is located in this portion of the structure. As you can see, the Venetoclax actually crystallized in two different occupancy states, and the major difference between the two was in this dimethylcyclohexene ring. Right, so the aza-indole interacts with the P4 pocket, and in the paper they show that this glycine residue actually mutates to a valine. So we're going to use Nanome's mutate tool within the modify menu to mutate that to the valine.
And when it becomes a valine, it makes it resistant to the drug?
Exactly, yep. All right, and so what they thought was that it actually forms a clash with this glutamate 152. So we can take a look at that in Nanome as well. Calculate clashes.
Oh, look at that.
Yep. So,
so Carla, when you turn on clashes, we can see that this glutamate and this valine are way too close to each other, as we see here in just the structure where we mutated it by hand. So that glutamate must do something.
exactly. So I'm actually going to turn on the torsion tool. And I think in the paper they talked about that it actually rotates down into the P2 pocket, which now can form a clash with the Venetoclax itself.
Yeah, so you've gotten rid of this clash, but now there's probably not enough room for this chlorophenyl to fit well.
Exactly. So that must confer the resistance to the drug.
And this is really interesting because this glycine that's now a valine is near the P4 pocket. So we might have thought that that mutation would have problems for the aza-indole, but as we see through this, through space interaction with the glutamate, it actually makes a problem for the P2 pocket way down here.
Right. That's actually pretty fascinating. So
yeah,
make it a definite.
Really nice work in this paper.
Exactly. Challenge for a new analog down here that maybe could form a salt bridge or something with that glutamate. So let's take a closer look. Yeah. Well, I don't know if it works. Speaking of, because an introduction like that would probably change the chemical properties of Venetoclax, let's just take a look at the structure of Venetoclax in a little more detail. Because it is a super large molecule, and it turns out it's very potent. I think it's picomolar against BCL2, but the resistance mutant was like 3 nanomolar, I think.
Yeah, so this is a really interesting drug discovery project from the scientists at Abbvie, which was called Abbott when the work started. The early BCL2 ligands were actually found through a fragment-based drug discovery program, one of the early famous ones. And when they first started publishing and presenting on these molecules, people were skeptical that you could get a good drug from these very large molecules. In the earlier one that went in the clinic did fall out because of side effects, but this one has a molecular
Cytopenia.
weight of, well, I guess we'll calculate it because I'm not even going to guess, but it's probably over 800.
It's pretty large, right? So yeah, through Nanome's stacks menu, we can actually turn on our chemical properties, which leverages RDKit, and I will activate that. And select Venetoclax. And you're sure right, Mike, it's almost 900 even, which is well over Lipinski's rule of 5, that's for sure.
And this log P is about as high as you see in a drug molecule as well.
But it is orally
And
bioavailable, which is
the
interesting.
topological polar surface area is enormous.
Mm-hmm. A lot of rotatable bonds. Yeah, definitely not something that might have jumped out to a med chemist as an obvious candidate, but certainly works really well.
But it's been
And I think it,
successful. And if you look, it is extremely highly plasma protein bound, over around 99.9%. And
oh,
for some molecules that can make it very difficult for them to have activity,
sure.
because you don't have much free drug. But as you mentioned, this is a very potent molecule.
Yep.
So maybe you don't need all that much free drug at any one time.
True. True. All right. Well,
So, Carla, you mentioned a possible analog that might work better on the mutant. Uh, should we see if we can modify Venetoclax to that compound just for fun and see what its properties would look like?
oh yeah, we can totally do that. I'll take a snapshot of the chemical properties here, so we can come back and look at this for comparison, and then using Nanome's MedChem tool, we can actually delete this root and okay, go back to build, and then yeah. So I don't know. We probably definitely want to incorporate a smaller ring. I mean, I don't know, a
Yeah.
cyclopentene, maybe. Um, maybe add a nitrogen to that. I mean, even like an imidazole may form
Yeah, I think imidazole would be interesting. That might,
a
if it twists the
salt
right way, it
bridge.
could make the salt bridge you mentioned.
Right, exactly. So we could try that. Definitely. So we can see that the properties updated in real time. It's a little bit less molecular weight. Um, but yeah, so I'll take a
And lower
snapshot of
log P.
this. So we can definitely compare the properties directly here in this table.
Yeah. Just for
Do
fun,
that
Carla,
export.
should we bring the structure of the protein back up?
Can definitely do that. I'll move this over here and lock it so we can keep it for reference. And then maybe if I turn on one of the other ones, I'll make all of this a bit smaller. We can try to align them a little better with each other. Probably measure the distance for that histidine too, right?
Yeah.
Or, sorry, imidazole. Okay. I'll turn off the other one. I'll lock this in place. So yeah, let's do that.
And that glutamate could twist a little bit more towards it if it was excited, if it wanted to.
That's true. I guess
if
we
it
should
saw
probably
potential to bind, I don't know.
move it around a little. Maybe something like that. Not really lined up exactly, but could just measure the distance. So it's, yeah, you could get a hydrogen bond there, I guess.
Yeah.
Not the worst
I think
idea,
that looks
maybe.
good.
And you never know if you get a bridging water too.
Was that about 3 angstrom? Yeah.
Yeah, yeah. They're not perfectly lined up. I
Very
mean,
nice.
I probably want to do a docking experiment to get them looking a little more
I
reasonable.
think
But
people watching this video are going to run out and try to make that compound.
that would be pretty cool.
Yeah.
This is what you can do in Nanome for sure. And it's, definitely a good place for ideation.
Yeah, that's excellent.
All right, thank you everyone for watching, and hope you enjoyed this. And now you can see how Nanome might contribute to your own drug discovery efforts. Bye.
Yeah, thanks everybody. Fascinating work by the scientist that wrote the paper as well.
Definitely, definitely.